Let's take a look at how to break a pencil. Although it may not seem like it, breaking this pencil can be a bit harder than you would think. There's many different ways, and we're going to analyze each and every single way. So let's dive right into it because this is great practice for an F equals M problem. Okay, so let's go into how to break a pencil. So the first way that we're going to analyze is breaking a pencil the not unintuitive way. I put a force like I clench my fingers like this, and then I try pulling on it. As we all know, that's not going to work. Now let's try to explain the intuitivity behind that result. So here I have my pencil modeled as a rectangle, and that's in a plane. So if you look at it, for example, like this, although to you, because you have eyes and you can interpret that depth, you see that this is 3D. If you think about it, it's just a 2D rectangle, right? So that's what we're imagining our pencil like. And if you're wondering why we haven't modeled it just as a straight rod, because, well, that's obviously way simpler to work with. In part 2 of this video, where we'll explain how we can break a pencil by bending it, we'll see that it's crucial for that us to represent a pencil as a rectangle or like a cylinder rather than a rod, because the radius of this cylinder, this distance, is very important. So I'll talk about that later when we get to part 2. So for now, let's see how we can work with this rectangle and how we break a pencil by clenching it, I guess. Okay, so let's analyze our forces. So there's 5 apparent forces, at least the most apparent ones, and then there's 4 other forces that will kind of result from our fingers' motion. So the first force is gravity, that stems from the center. That stems from the center of the pencil, and we're assuming that the pencil has a uniformly distributed mass, and if it didn't, in real life it doesn't, but it won't affect this problem very much because it's close enough to uniform. Okay, and then we have our 4 forces from my fingers. So if you look at it, this finger applies a downward force, like on this end. My thumb, my left, your guys is right. This thumb applies a force upwards, and then my right finger and your left finger, the top applies a downward force, and the same thing for the bottom. So we can write all these forces out like such. We'll have a downward force on both sides of the top, and we'll have an upwards force on both sides of the bottom. So for symmetrical purposes, we're going to assume that the forces on the left and right are equal. If they weren't equal, that would actually generate a torque. I'm going to talk about this later, but the pencil must stay at rest. I can't physically break a pencil if it's moving around like this. It's too hard to control my movement. And if this force, the force on the right was greater than the force on the left, that would actually generate a torque. And that would disable me that would make the pencil rotate, and it make it harder to do whatever motion I want. Okay, and then on the bottom, so it's important to note that the forces on the bottom will not actually be the same as the forces on top, and we can explain why later. Okay, so the force on the bottom will be F2. So as we said, the forces on the pencil must balance out on the general pencil. So there's no horizontal forces in this diagram. We're going to add those in later. But for vertical forces, we must find that 2F1, actually let's start 2F2, the upwards force, must equal the downwards force on the pencil, 2F2 plus mg. Okay, that's one of our most important equations. And now we'll talk about the horizontal forces that this pencil will experience. So if you look at it, if you imagine that if this other hand wasn't there, when I'm trying to break a pencil like this, I'm moving my fingers to my right, your guys' left, and same thing for the other hand. And now when I have both hands, they're opposing this force. Like one force is pulling it that way, this way, the other force is pulling the pencil that way. And this force stems from friction. When I'm doing this, the pencil plays catch up. Its direction is the opposite of the motion. In my finger's frame of reference, my pencil, if there were no friction on it, would actually be moving that way, that way, that way. And now, and so the friction will point in this direction, yeah, in this direction to make my pencil follow with me. So, let's see what these friction forces are. So over here, at this point, there's a friction force of F1 mu. And over here, there's a friction force of F2 mu. Because F2 is the normal force on this point, and F1 is the normal force on this point, and mu is the coefficient of friction. It's static friction because we're assuming that our my fingers are not moving relative to the pencil. Okay. And it's going to be the same thing on the other side, but in the opposite direction. So F1 mu s, and over here, F2 mu s. And you'll see that the horizontal forces cancel out. Obviously, this one will cancel out this one, right? And so on, for the bottom one. Okay, so now you understand. Now you might be wondering, well then, how do you know if the pencil's breaking? I mean, we just get that the forces of the pencil are balanced. What makes it break? So the key observation here that will also apply in part 2 is that we can think of the pencil as having two different rods, kind of. The left and the right. And we can divide it where the pencil will break. So if we're just saying, we can just say that the pencil will probably break in the middle. So we're going to divide the pencil like such. So we'll divide it like such so that this rod is a separate entity than the right rod is a separate entity than the left rod. But then what's holding the rod together when what's holding the entire pencil together when I'm moving this around? If the right rod is different from the left rod? Well, there is a force like this. Sorry. So there's a force on this rod, so now I'm just going to draw the right rod because I'll make things simpler. So that's the right rod right there. And then we have a downward force of F1. F2, I'm going to ignore gravity because gravity is really, that's the only thing that we're using this rod for is for the horizontal forces. So I'm just going to ignore gravity in this scenario. We'll have F1 mu s over there and F2 mu s over there. Okay, and then the force that's opposing this, we can call this Fm. And Fm or F max is the maximum force that the joints or the bonds or whatever you want to call it between the right rod and the left rod can take. So because of the way the wood is made and whatnot, there are forces that keep the left side of the rod and the right side of the rod together. Otherwise, well, yes, the left side and the right side would just fall apart. But the left side and the right side don't fall apart because there's a bond holding the extreme edge of the right side to the extreme edge of the left side. And that force, we don't know what that is because it's like dependent on a variety of things, and there's no point in calculating that. It's dependent on its changes for every single pencil. We're going to call that Fm, the maximum force that the pencil can take before it snaps. Okay. So, well, if you must know, one thing you want to notice then, we want to generate some sort of motion in this rod so that if we generate some motion in this rod, that means it breaks. Because if the right rod has some motion, then that means it's gone away from the other side of the rod, which means it's broken. So what we want to overcome is this force. So we want to say that F1 mu s plus F2 mu s, the forces due to friction, we want this to be greater than Fm, which is the force holding it back because of the strength of the wood. Okay, so now remember how we had this up top? I'm sorry, this should be F1. I don't know what I was saying or what I was writing. So now we can use this to substitute F2 into here. So we only have one unknown variable. So for solving for F2, we find that F2 is equal to F1 plus mg over 2. And if you plug that back into here, we look at that F1 mu s plus F1 mu s plus mg mu over 2 must be greater than or equal to Fm. So now let's solve for F1, or the limits of F1. So in order to break it, F1 must be greater than Fm plus mg mu s over 2 mu s. Okay, so that's the defining force. That's the defining limit on the force. If we exceed this force on the top, then we will guarantee to break the pencil. Now, this top force is really strong, and one thing to notice is your hands are slippery. It might not seem like that to you, but they're really slippery. Your hands are naturally oily, and because of your hands most likely being smooth, your coefficient of friction is not that high. It's probably low, which increases this force even further. Ideally, we'd actually want this to be less than Fm, and ideally we want to be way less than Fm. And that can happen when we'll talk about in part 2, where we can break the pencil using this tension from bending it. So we'll talk about that later in part 2. Stay tuned for part 2, and we'll see you guys in the next video.